All right. How you guys doing? Doing okay? So if you happen to notice, last time we had some internet issues. Probably noticing right now our Wi-Fi is not great. So the recording from last lecture lasted 20 minutes and then was gone. I didn't notice that while I was recording or while I was streaming. So this time and in the future, I'm going to aim to record in addition to putting it live so I can upload it. In the meantime, you have the 20-minute video bit of the lecture from last time, and on Moodle I put a link to last time I taught the equivalent of that lecture. It should be pretty close. I do try to review and might have been in a different spot during the course or something a little bit, but it should be the same content approximately. Okay, so that's available to you if you missed it or need it. And I'll try to make this specific. These will be kind of included into your grades eventually. Again, this is kind of just practicing, and I have to file something with LSU to say, hey, XYZ people were here, I confirm. Okay, so that's the purpose right now. Anybody need another moment for this? Okay, so go ahead and do that. Today we're going to pick up where we left off with the development of a mass balance equation. We kind of cut short a little bit last time on that, so I'm going to give us a moment to take a look at not just the batch reactions, but also what happens if we have some flow as well. So practicing connecting the reactions with the reactor itself in order that we have a conservation of mass, okay? And then from there, you could solve for the time it takes or for the amount of chlorine it takes or something like that. Okay, so with that, I'm going to come back to our slides where we left off. So we were talking about the mass balance for a batch case. I gave you a chance to take a look at this, begin deriving it. We wrote all these notes and ultimately said we can find a solution for the concentration of a given substance as a function of time. Now what you'll note is you could solve this for time instead of concentration. Maybe you have concentration, you just need to know how much time it takes. In fact, many times that'll be the case. We want to target a specific endpoint concentration. I don't want any more than this number of viruses in my water per liter because I know that'll be protective of health. Therefore, how much time does it take? Okay, so sometimes we will take a mass balance and solve it for something else other than C. Perhaps we'll solve for the time. We could solve for the rate constant. How efficient does this reaction have to be? Or maybe we know everything about the reaction except we don't know the constant, so we could solve for the constant. So all that to say we can develop this mass balance relationship and then use it for whatever piece of information we need. Okay? And sometimes we'll have to do that in order to solve for something else, to apply it. So these mass balance equations are going to be a lot more useful than just solve for C, okay? Although that is something we can do. All right, so we did the batch case, and as I told you, that's approximately the same as the plug flow case, as assuming we take it like a batch on a conveyor belt, and it pours out at the end, okay? Now, it gets a little more complicated if we do, but just noting it here, I'm putting a comma there because I'm just saying we both have both of those. So don't get confused by how I'm writing that. I could also write this as Q and a C naught, just saying that those are there. All right, so given that, take a moment and see if you How are you feeling? Getting somewhere? Getting confused? A little confusion. Flow rate Q times the influent concentration C naught. Minus the output rate, that's again the same flow rate, times C, the concentration leaving. Now that C is also the same as the C that's inside here. So we have C inside the reactor. Here I would make it look kind of like this. It's a well-mixed reactor. We have some volume in here and also some concentration C. Okay, so that's just expanding that a little bigger. I'm going to erase this in a minute so I can make room for the other side. But for the moment, this is what we're looking at. A QC leaving and a Q and a C naught coming in. All right, so those are our flow terms, the obvious parts. Then we have the reaction term. And this reaction is happening inside the context of the volume, so we need a volume term there. So this will be, I put plus the reaction, so plus V times however C is reacting, the R of C. Now here's where you need to remember, and I have a reminder right here, that for a zero order decay reaction, we'll add a negative in there to say we're decreasing. And because it's a zero order, that means the way we describe this reaction is the rate constant times the concentration to the nth power, where nth is the reaction order. So it's a 0th order, so this is C to the 0. That means this is essentially minus K. So when we rewrite this, we'll say this is equal to QC naught minus QC plus a negative V times K. C to the 0 power is 1, so I'm just going to write it as 1. Okay? Yeah. I didn't say that they're equal. Oh, sorry. The Q itself. Sorry, QC naught is not necessarily equal to QC. The Q's are equal because we have no. We're going to assume we're not gaining or losing water inside the system. So if our water stays at a constant volume, then the Q's have to equal because there's only one Q going in and one Q going out. So great question, and I'm sorry I misheard it at first or misunderstood. So the Q's will almost always be equal. If we just have one going in and one going out, I'm never going to give you a problem where the volume of our reactor itself is changing, or we're having some unknown source of water leaving or coming in. You can imagine that could be a pretty challenging situation if you have a leaky reactor and you're losing volume somewhere, then your whole steady state assumption goes out the window and your math goes out the window too. So there would be challenges if Q's did not add up nicely. We're not going to do that. And in most cases, it makes sense if we have, yeah. So the VDC is like the accumulation rate? Yeah, so the accumulation rate, we are always going to write as in that volume, the change of concentration over time. A lot of times we'll set it to 0 with a steady state assumption. But even if we look back from last time in the batch case, that's exactly how we started, saying, okay, in that volume in the batch situation, how is that concentration changing over time? V times dC over dt. Okay, does this part make sense so far? All right, so now we will say at steady state, well, let me just take a moment to say, if we kept this at V dC dt, you can see we have some sort of integration coming, right? We'll have to perhaps separate C and figure that out, do a little bit of calculus, and in a 0 order, it should turn out to be quite simple. But it's even more simple if we're at steady state. So steady state means that even if we're changing the amount of C in the water, the total mass of C in our reactor is staying steady. We've been doing the same process for some time, and so we're not accumulating or increasing or decreasing the total amount of C in our reactor. So that means V dC dt equals 0 because there's no change over time in C within that control volume that we defined. Yeah.
Can you just assume it's going to be 0 every time?
If we steady state, yes. Sorry, I cut you off.
Yeah, no,
Okay, yeah, if you see steady state, that's exactly what it means. Always that's what it means. So then the only case to watch out for is if it's not steady state, or if we have a batch reactor, it can't be at steady state if there's some net reaction happening. You're going to have that there. But this means we can simplify and say 0 equals QC minus VK. So we were tasked to solve for C, so we can add QC to both sides. We'll get QC equals QC naught minus VK. Divide everything by Q, and we will get C equals C naught minus V over Q times K. And what is V over Q? Heard some of it? Okay. This is theta, our hydraulic residence time, right? So, okay, so I'll set the problem up with you. Has to go in here. That's kind of how we're navigating this. All right, got an answer? Close to an answer? Just a little bit of algebra from here where I've got it. Is this process making some sense to you? Kind of getting it? Okay, this is fundamental to the entire class. So if you can master this stuff, that'll be very good news for you on all the problems in the future, because this is the basis for almost all of the class. This type of, okay, here's some reaction, here's some context for it, let me assemble this mass balance to put things in the place that we need them. So we'll go ahead and solve for C here. We notice that we've got two terms with C in it. So I'm going to get them on one side by adding them both to both sides of the equation. And I'll go ahead and separate. We'll factor out the C. VK equals Q C naught. Now, one thing that you might notice is we could have divided everything by Q, kind of simplify things a little bit. And maybe we'll go ahead and do that. We'll just divide everything by Q here. Could have done that in a previous step. But if we do that right now, we'll get C times 1 plus, here's that theta again because it's V over Q. Theta K equals C naught. You don't have to divide by the Q there. You could do it later. You could do it earlier. You don't have to divide by it at all. I just find it makes it a little simpler. So then we can get C equals C naught over 1 plus theta k. All right? So in some sense, this would be the solution to the mass balance, or rather we have derived an equation for C as a function of the hydraulic residence time, the rate constant, and our initial starting condition. Now, a lot of times we're actually going to be interested in C over C naught. So how much do we have there compared to how much we started with? Sometimes in the case of, right, to remember how to deal with the integration of 1 over C squared dc, or